Yes.
Are you sure that the live stream is working? Because on my side, I opened YouTube and it still says waiting for.
Really?
Yeah,
I don't know. I have. Yeah, I think so.
Yeah. It's now it works. So sorry.
Oh, okay. For whatever reason, it took some time to start. That's unfortunate.
Yeah. All good.
Thank you, Tobias. Yeah. Anyway, I will continue. Yeah, as I said, these compute DRAM the authors of compute DRAM were able to by using softNC, were able to execute row clone and bitwise operations inside real DRAM chips, inside off-the-shelf chips, and this was relatively simple, or as simple as playing with the timing parameters and violating timing parameters in order to copy one row from one row to another row, or executing these, or activating 3 rows in order to execute bitwise operations. Remember as well that we presented a project from us that is called PyDRAM that provides a flexible platform to explore end-to-end implementations of processing using memory techniques. And PyDRAM is as I said, end-to-end platform that includes hardware components and software components as well, as you may remember from this slide here. We implemented PyDRAM on FPGA. Essentially, in the FPGA, we implement our RISC-V core, and from that core, we can access the compute-enabled DIMM, which in the end is off-the-shelf DRAM memory that is compute capable, because we use the same ideas in the compute DRAM paper to enable operations like row clone. But remember that we had Ataberg, the first author of PyDRAM, who was an invited speaker in our meeting 6. And if you want to review this PyDRAM project, I would recommend you this lecture. And also remember that the paper is publicly available, as well as the source code. So hopefully many of you will find this PyDRAM platform as a useful tool for your own research. Okay, so after we have covered, let's say, the real world examples and prototypes, we also talk in this course about how to program these architectures, yeah, very briefly remind you about the UPMEM PIM system. Remember that the UPMEM PIM system contains this main memory that is a conventional DRAM that keeps working as the main memory of the host CPU, and we also have the PIM-enabled memory. Remember as well that programming this UPMEM system is kind of a combination of a distributed system and a shared memory system. It's distributed from DPU to DPU because all the DPUs have access to their own memory space, that is their MRAM. And but inside each of the DPUs, we have multiple threads, up to 24 tasklets or software threads that are running and accessing this single shared memory space that is this DRAM bank. And remember as well that the tasklets running on the pipeline can synchronize and can communicate using synchronization primitives and using WRAM, which is the scratchpad for operands. Remember as well that programming the UPMEM PIM system requires us to use the accelerator model, because we have to explicitly move data from the memory of the host processor to the memory of the accelerator, and we need to explicitly launch the execution of the kernel onto the UPMEM processors. Here is a flow diagram of how this happens. While the data is being processed by the DRAM processors, by the DPUs, the CPU doesn't have access to the MRAM banks, but is continuously checking for the completion of the kernel. So it was important, remember as well, key programming recommendation in the UPMEM system was to try to minimize the amount of communication or the communication needs across the DPUs, because all communication happens through the host CPU, and that's quite costly according to our analysis, at least for specific benchmarks that really require, you know, a lot of back and forth communication. For example, for redistribution of intermediate results, we talk about interesting benchmarks, for example, BFS for you know, graph processing. And if you want to recall how to program the PIM architecture, I can recommend your meeting aid or lecture aid where we talk about it. We also talk about how to program a completely different architecture, that is the SIMD-RAM framework. In the SIMD-RAM framework, give me 1 second. In the SIMD-RAM framework is a framework for processing using memory. Remember that SIMD-RAM allows us to create arbitrary, completely new operations and integrate them into the system by creating the corresponding sequence of commands, of different commands, and then and having this enhanced memory controller that can read microprograms and start issuing the necessary commands to the DRAM side in order to execute the bulk bitwise operations. And we also studied here how to program a SIMD-RAM capable system using the SIMD-RAM ISA extensions. Remember that we have specific instructions for initialization or for predication, and then we also have instructions with 2 or 3 input operands. No, actually, it's 1 or 2 input operands, and that are configurable. Let's say we can create different arithmetic operations or even more complex ones. And we covered this example here where we saw how to compile or how to translate some C code, high-level language code, as for example, this simple loop where we go over 2 arrays, and depending on what's the value of one of the value of the corresponding element of one of the arrays, we perform an addition or a subtraction, right? And we were explaining how this translates into a sequence of BBOps that are the SIMD-RAM instructions. But if you want to recall SIMD-RAM, we also have a specific lecture about SIMD-RAM, which was lecture 10, and here you have the link to the recording. Okay, I don't know if you have any questions. If not, I will continue. Yeah, another important thing to discuss here is to what should the runtime in a system where what should do the runtime in a system where we have processing in memory capabilities? In the end, this runtime system is responsible for doing scheduling, meaning offloading computation to the PIM side whenever it makes sense to do that, and also doing the necessary code and data mapping. And that will be very much dependent on the specific processing in memory system. We have actually studied some of these also in this course as well. I want to first remind you one of the proposals that we covered here, and we can extend a little bit more later. Remember that in our first lecture, we talked about PIM-enabled instructions. That was kind of a seminal work that proposed extending memory with very simple compute units that can execute individual instructions that are especially memory bound, that are especially memory intense, and require a lot of bandwidth consumption. We talk about the example of the PageRank algorithm, where, remember, the memory accesses are typically very random, while the computation itself is very lightweight, right? And you might remember this slide where we see that updating the rank of a specific node in our graph requires to probably read 64 bytes from memory and then write back these 64 bytes for maybe just a single addition, right? And the idea that the PEI paper proposes is to replace these update operations with something like a specific instruction that is executed on the memory side in a way that we reduce the amount of data movement. For example, for PageRank, we can reduce from 128 bytes in and out from memory to only 8 bytes in to memory. And this is an example PI Micro Architecture. Remember that our system is expanded with some PCUs that are the units dedicated to execute the PIM enable instructions. PCU here means PEI computation unit. But the interesting thing of this proposal as well is that it does intelligent scheduler, because it includes this locality monitor that can check where a cache line resides, whether in the CPU cache hierarchy or in the main memory. And depending on that, it will schedule the corresponding PIM enable instruction either on the host processor or on the memory side. And by using this intelligent scheduling, it's possible to increase the performance improvements and the energy savings from this system. And that's actually something that you can see here in this screen, in this slide. This is for performance, and this is also for the energy consumption. Notice how the locality aware execution, it even outperforms the PIM only approach, even with the largest data sets that don't fit in the cache hierarchy of the CPU. And if you want to review the paper, remember that here you have links to these paper slides and so on. But yeah, that, as I said, it's not the only work that covers the needs for doing intelligent scheduling, right? So in a completely different environment, in a GPU that might be extended with processing in memory capabilities, we also need to deal with where specific operations should be executed and how we need to map data in order for the processing in memory cores to access data in the most efficient way as well. So here in this figure, for example, you can identify a main GPU similar to the ones we use these days, connected to different memory stacks, which is also something in common with the current GPUs that use HBM2 or HBM2E memory, and in the end, when we access data from the main GPU, we don't really care about where this data is mapped, because the main GPU has several memory controllers, and depending on where the some data, some array resides, it will use the corresponding memory controller to access the data. But when we have a system like this that is extended with GPU cores in the logic layer of the memory stacks, it's important to first discuss, or first to figure out, where are we going to execute a specific piece of code, whether in the main GPU or in the GPU cores near the memory. Or also important thing here is how to map data, because if you have, let's say, certain processing elements here that need to access data that resides in the global memory of the GPU, you want that data be in the same stack, because otherwise these guys will have to go all the way to another stack, which probably will take significant latency and will be an important overhead for the execution of the program. So these scheduling decisions and also these data mapping decisions are very important for the different processing in memory proposals, and also might be specific for the different processing in memory proposals as well. Hopefully, we will be able to come up with, let's say, general rules on how to do scheduling, on how to do data mapping, in order to, reuse these kind of techniques or policies or heuristics for different systems. But anyway, in the meantime, you can read this Tom paper that was presented at DISCA 2016, and it's definitely a very interesting proposal. And a related proposal as well also for GPU architectures is this scheduling techniques for GPU architectures with processing in memory capabilities that was also like contemporary with the previous one. Similar approach in some sense, but the interesting difference between these two is that they schedule code on the memory side or on the regular GPU side at different granularities. So there are different trade-offs and different design considerations that it's worth studying and comparing these two proposals. And also a couple more works that discuss and deal with this scheduling of code. The first one is accelerating dependent cache misses with an enhanced memory controller. And the second one is continuous run ahead transparent hardware acceleration for memory intensive workloads. Two highly recommended works as well. But as I said, there is still a lot to do in this topic. Many research questions that we still need to answer. Some of them are related to the mechanisms to enable and disable PIM execution, depending on what are the characteristics of the specific workload that we are executing. Questions as well related to mechanisms to identify when parts of particular application can benefit from processing in memory and performing the scheduling in the right manner as well. And also other considerations related to, for example, how to share processing in memory engines, processing in memory cores when we have the multiple requesting cores that might belong to the same application or maybe completely different processes. And observe that these also opens not only interesting, mechanisms for scheduling decisions, but also security considerations that need to be taken into account and hopefully will be studied as well in the near future. And simple mechanisms as well, how to manage the access to a memory that serves both CPU request and PIM request. And again, this relates to efficient access to memory, and also there might be some security considerations as well. Okay, let's keep talking about the next of our topics that we are going to cover today. I mentioned in the beginning that we need system support to enable the adoption of processing in memory, and among these different things in the system support, we need to provide memory coherence. We need to make sure that the data that is accessed by by the host CPU and the data that is accessed by the processing in memory elements is the most up-to-date version of the most up-to-date copies of the data. And that's what the memory coherence mechanisms should take care of. But implementing efficient memory coherence mechanisms in systems with processing in memory capabilities is not straightforward. It's not that straightforward also in multi-core systems, for example, with no processing in memory capabilities. So it's even more complex when we have processing in memory cores. And actually, we did some study on this, and here in this slide, for example, you can compare the execution of the performance of a CPU PIM system containing, implementing, let's say, traditional approaches to memory coherence, like fine-grained memory coherence, for example, the MESI protocol, coarse-grained memory coherence, or no coherence at all, and you can see here that if they provide some speed up over the baseline is actually pretty low only in this case, and actually they are very far from the ideal execution, from the whole potential of processing in memory, right? That is this yellow bar. So it was clearly necessary to propose a new mechanism to maintain the coherence in a CPU PIM system. And our group published a couple of papers about this. The first one was lazy PIM And the second one was Conda, an extension of this lazy PIM proposal. I'm going to very briefly review or introduce you to Conda in order for you to understand how we can enable coherence support in systems with near data accelerators or in general processing in memory capabilities. So we know that specialized accelerators are everywhere, and now we can talk about a new way of doing acceleration that are near data accelerators or in general processing in memory systems. Maintaining the coherence for systems with processing in memory capabilities and CPUs is challenging. The first reason for that is that there is a large cost of chip communication. So whenever we need to maintain coherence between this compute unit and this CPU, the cache hierarchy of this CPU, we are going to need to go through the memory bus. And as you know, this is where the main problem of current computing systems, or one of the key problems of current computing systems, resides, the large cost of the off-chip communication. And also PIM applications generate a large amount of off-chip data movement. So it's impractical to use traditional coherence protocol. Existing coherence mechanisms are not good, as we have seen in the previous plot, in the previous graph, because these mechanisms eliminate a significant portion of the benefits of processing in memory, because they incur a lot of cheap coherence traffic that is in principle unnecessary, and also because it would be possible to eliminate a lot of this off-chip traffic if the coherence mechanism had some insights into the memory accesses. So the idea here is to propose an optimistic approach that can, first of all, gain insights before any coherence check happens, and performs only the necessary coherence request. So we try to minimize as much as possible the coherence traffic, the communication due to maintaining memory coherence. And this is Conda, an optimistic mechanism that enables memory coherence in systems with processing in memory capabilities, avoiding all unnecessary coherence traffic. The key idea in Conda is to offload the PIM kernel to the PIM side and perform optimistic execution on the PIM side, which means that there is no coherence request. We simply assume that things are going to go well. And at some point, when the execution terminates on the PIM side, we generate a signature that is somehow collection of the memory accesses that the memory side has performed, like a summary of the memory accesses that the memory side, the PIM side has performed. And this signature is sent to the CPU to be compared to the own signature of the CPU and figure out whether there are any coherence problems or not. So this is why we have here this coherence resolution stage where the CPU decides if the optimism was good or not, right? So based on that, it will commit, let's say, give the execution on the PIM side for completed, and or re-execute, meaning that things didn't go well and we need to cancel, let's say, the previous execution on the memory side, and then re-execute again with valid data. Conda showed very interesting, very good performance and energy improvements, as you see, very close to the ideal coherence mechanism. And I can, recommend you to take a look at the paper that was presented at ISCA 2019. We have also talked in this course about another important topic that we mentioned again today is the synchronization support. I don't really need to spend much time on this because our previous lecture was about this, was Synchron. There's a talk, the interesting talk that Christina gave last Tuesday. But for those who were not in the meeting, I would like to very quickly go over Synchron as well. So Synchron proposes efficient synchronization support for processing in memory architectures. We know that synchronization is challenging for NDP systems, and prior schemes are not suitable or not efficient for processing in memory systems, and that's why we contribute Synchron that, as you can see, provides very good performance and energy results compared to an ideal zero overhead synchronization scheme. Synchronization is necessary, as you know, many important applications like graph analytics, for example, an application like single source, shortest path. We will need to acquire logs in order to, and release them later in order to update some common data structure, like for example this array of distances that tells us what's the distance between a specific node of the graph to the source node. But synchronization is also necessary in many more applications as well. We assume in this Synchron paper, as you may remember, a baseline NDP architecture that is composed by NDP units, and each of the NDP units has multiple NDP cores. Observe that this is pretty similar to previous architecture proposals like Tesseract, or like even the UpMem architecture itself is kind of similar to this one. And the main challenges that we have in this kind of system when it comes to synchronizing the different processing in memory cores is, first of all, the lack of hardware cache coherence support. By the way, observe that in the previous section of the lecture, we talked about coherence support, but it's coherence between the main CPU, the host CPU, and the processing in memory side. Here we are talking about lack of coherent support in the processing in memory side itself across the different processing in memory cores. And also the communication across NDP units is expensive, because in the end it's off-chip communication, and also because these are, in general, we can consider them distributed systems. There is a lack of a shared level of cache memory, and also in general a lack of shared memory. So many of the synchronization approaches that have been proposed in the past based on shared memory are not useful in this environment, in this context. So message passing synchronization approaches make much more sense. And here in Synchron, we propose a specialized hardware that is going to support synchronization in these kind of systems. So yeah, each of the NDP units is extended with a synchronization engine. This idea skips any complex coherence protocols, no need for atomic operations, and actually it has pretty low hardware cost. The synchronization unit, as you can see, is composed by a processing element, a processing unit, and also a synchronization table and indexing counters. In this synchronization table is where we are going to keep track of the synchronization requests, like for example, a log acquire coming from the NDP cores. And this is going to be pretty efficient, because there are no accesses to the memory, to the memory of the NDP unit, and it's also low latency because the synchronization engine is right next to the NDP cores. And Synchron allows us to perform hierarchical communication. And what that means is that the synchronization engines in each NDP unit collect the synchronization requests from the different NDP cores, and then at some point they will send like a global request to a master synchronization engine that resides in one of the NDP units. So this hierarchical approach minimizes expensive communication, as you can see. So in the end, Synchron provides high system performance, low hardware cost, programming ease, and general synchronization support, and also very good results with compared to an ideal zero overhead synchronization mechanism. If you want to learn more about Synchron, please read the paper, or for sure watch our previous lecture that was delivered by Christina. Related to synchronization as well is the access to concurrent data structures, and in that sense, I can recommend you this interesting paper where the authors explore how to implement efficient concurrent data structures, like for example, FIFOs, linked lists, skip lists in processing in memory systems. And another important part of the system support that we need for the end-to-end integration of PIM systems or of PIM capabilities is the virtual memory support. And again, same as other topics or other aspects that we are covering today, like for example, the scheduling, this might be, the virtual memory support might need to be tailored for the specific PIM system, right? If you think about something like PIM enabled instructions, in PIM enabled instructions, we are offloading individual instructions to the memory side. So in the end, doing the virtual to physical memory address translation, it's relatively straightforward because it's for a single instruction. This virtual to physical memory address translation can be done on the memory side, on the CPU side, and when the instruction is offloaded to the memory side, we are offloading the instructions directly with physical addresses, and that's going to be pretty efficient because we don't need to worry about virtual memory translation on the memory side, right? And if you think about like some processing in memory coarse-grained accelerators, such as, for example, Tesseract or even the ADMEN PIN system, they are directly using the physical address space. So there is no need for virtual memory support in those systems. But in other systems, especially in cases where we are going to have concurrent access from the CPU side and from the processing in memory side, or we have a direct access, like the processing in memory, the PIM enabled memory is the main memory itself, we need to have this virtual memory support. And as I said, the way that different works have proposed virtual memory support depends on the specific needs of the particular proposal. Today, I want to talk about one interesting work that really, pays a lot of attention to this virtual to physical memory address translation because it's a way of accelerating pointer chasing applications in processing in memory. And pointer chasing applications require a lot of memory accesses, usually very regular memory accesses that make more challenging to do this virtual to physical memory address translation. And this is the, let's start with the executive summary of this work. Accelerating pointer chasing inside main memory is the main goal, but there are challenges. First of all is parallelism. Second is address translation challenge. As I said, the solution is this proposed in memory pointer chasing accelerator called IMPICA. The key idea of IMPICA is to do address access decoupling. There are going to be two different units, one to calculate addresses, the other one to access the memory itself. And this enables parallelism in the accelerator with low cost. The accelerator is extended with a page table, a low-cost page table in the logic layer that facilitates the virtual to physical address translation. And as you will see, quite interesting performance results and reduction in energy consumption with respect to the baseline CPU. But let's motivate a little bit. Linked data structures are widely used in many important applications, like, for example, databases, B-trees, key value stores, hash tables, and so on. And these linked data structures are connected by pointers. So traversing these linked data structures requires chasing pointers. And here you have an example of what needs to be done by a CPU when it needs to traverse a linked data structure. So for example, imagine that we want to find A and we have this tree. So because these different nodes of the tree are connected using pointers, we need to first access the first node, the root node, that is H, obtain the data, that is the contents of this node H, and there we have a pointer that points to the next node, the child E. So we have to go to memory to read E and bring E to the CPU, and then we can access A and we can retrieve the data of A. So as you see, in order to find A, we have to perform 3 accesses to memory, and we have to go back and forth 3 times, which is pretty costly in terms of latency, right? So we have serialized and irregular access patterns, especially because these trees will have an irregular or might have an irregular data structure. It's likely that we will have irregular access patterns, so we cannot benefit so much from the spatial locality. And in the end, these workloads might increase the number of cycles per instruction by up to 6 times, as we saw in the motivation of this work. So the goal is to accelerate pointer chasing inside memory in a way that we can save many of these memory accesses. For example, imagine that we need to find A in a system that is PIM enabled. It has compute capabilities in memory. If we need to find A, only thing to do is to send the request to the CPU, to the logic layer of the in the memory side, assuming that we are using a 3-stack memory. There we are going to have the accelerator that does the pointer chasing, and then we can retrieve the data. And as you see, instead of having 3 accesses to memory, as we saw in the previous example, here we only have a single access. And but there is a parallelism challenge. Why is that? Because normally when we have CPU cores, we'll have to, we first compute, then we access memory, then we compute again. And usually these accesses to memory, as you know, take much longer than the computation. And in memory accelerator, we can at least reduce significantly the latency of these memory accesses, right? And this, it's great because gives us some potential for gives us some potential for performance improvement. It can be faster for one operation. But the point is that in CPU or in the host system, we may have many CPU cores, and these CPU cores can execute in parallel, right? And they can access memory in parallel as well. So if we do the same, or if we try to do 2 accesses in the memory accelerator, in the end, we will have to do them one by one. And what that means is that it will be slower for 2 operations, right? Because we cannot parallelize the execution as we do from the CPU side. So the opportunity here is designing the accelerator in a nice way in order to save a lot of latency, a lot of time when accessing memory. So notice that the access to memory itself is usually much longer than the computation. And so here, the idea is to decouple the accelerator, the pointer chasing accelerator, in a way that it has 2 different engines. The first one is the address engine. The second one is the access engine. With the address engine, we perform computation and calculate addresses that are going to be used by the access engine in order to access memory. So this way, we can exploit the parallelism, and we can overlap the accesses, the computation and the accesses to memory. And this way, we will end up saving a significant amount of time with respect to the execution on the CPU. So this address access decoupling enables parallelism in both engines with low cost. Here you can see a simplified representation of the Micro core architecture with the address engine, with the access engine. In the middle, we have an access queue for them to communicate with each other, and a response queue. And they also are extended with a small cache that can save some of the accesses to the DRAM. So when it comes to integrate this Micro accelerator into the system, we will have the CPU sending requests to the accelerator, like for example, this traversal 1 and traversal 2, that will go all the way through the address engine and the access engine. And from the access engine, they will go to the DRAM, bring some data back, and move it to the address engine, as you see. So this is more or less how the Micro core is going to work with the decoupled engines, as you see. But now there is another challenge, this address translation. So in general, in CPUs, we use TLBs, we use the memory management unit to perform the address translation. So if we have a pointer in the virtual memory address space, we will have to do page walks. We'll have to go to the page table. And this means normally we have several levels of page tables. So normally we will have to perform several walks, right? And these require several memory accesses, 4 memory accesses in the example that we have just seen in the slide. And in the end, we will obtain the physical address. But as you see, this is pretty costly from the host side. And also one problem is that if for our in-Pica core, it's going to be an issue because there is no TLB or memory management unit on the memory side. And duplicating them is going to be costly and also creates compatibility issues. The page table walk requires multiple memory accesses, as you have seen. So we should try to come up with a better solution for this. So the key idea is to decouple the page table of the in-Pica side of the accelerator from the page table of the CPU, or in a different, expressed in a different manner, part of the page table of the CPU is reserved to the processing in memory side, what we call the in-Pica region. So what that means is that all virtual pages that are going to be used by the or accessed by the in-Pica accelerator, the in-Pica core, are going to reside in this in-Pica region in the virtual address space, and they can be mapped in wherever in the physical address space. So in the end is what we call a partial to any mapping, partial because we are not considering the whole virtual address space, but just a region of it that is assigned to the in-Pica accelerator. And here you can see how to access, how to obtain the physical address in a much simpler way as it's done with the page table workers in a CPU. We just need to use the addresses, the bits in the virtual address to access the, first of all, the bits that for the in-Pica region. Then we have this flat page table that is for large pages of 2 megabytes, and then we have a small page table for smaller pages of 4 kilobytes. And this way we obtain the physical address, because this region table is pretty small. It's mostly most of the time is going to reside in the in-Pica cache, and then this flat page table saves 1 memory access because it's handling these large pages. Here you see the evaluation methodology and some performance results. This is the speed up of in-Pica with respect to our baseline, a CPU with an extended, with a larger L2 in order to do a fair comparison. And we see pretty interesting speed ups, up to 90% faster execution on the memory side for linked lists. This is like let's say more real world benchmark. That is a database like with 2 different baselines. We see that the in-Pica is like significantly faster and also reduced latency as well. And in terms of energy consumption, we also see similar trends for the database and also for the micro benchmarks as well. Kind of pretty interesting energy savings. And the area and power overhead is relatively small, as you can see in this slide. But if you want to see all the details of this in-Pica proposal, please take a look at the paper presented at ICCB 2016. But that's not the only work that, as I said before, deals with virtual memory and processing in memory systems. In the end, virtual memory requires a lot of thinking, requires a lot of redesigning the virtual memory system in order to adapt it to a system that now has compute capabilities on the memory side, right? And one proposal that, in our opinion, can be very beneficial in this context and can help a lot for this kind of processing in memory proposals is the virtual block interface. As you know, in a conventional memory system, in a conventional virtual memory system, we have a virtual we have kind of a monolithic virtual address space, right? Where each of the processes running on the system have their own virtual address space. All of them are same size. They need to use page tables. We have seen in the previous slides, these page table walks are extremely costly. So this, let's say, traditional approach doesn't seem the best fit for new application. I mean, new scenarios such as processing systems with processing in memory capabilities, or virtualized environments, or systems with hybrid memories that require hybrid memory management, and so on. And so what BVI proposes is to have different VVI address spaces that can be accessed by different processes as well, and also these BVI address spaces are completely configurable. These are the virtual blocks that are have a size and characteristics as defined by the processes and required by the users. And then we have a memory translation layer in the memory controller that performs many of the operations that still these days are done by the CPU, by the OS in software, and are extremely costly. So this is kind of an efficient solution for many modern systems, and hopefully it will be widely applicable in the future as well. But if you want to learn about the virtual block interface, about BVI, please watch this lecture that Nastaran, the first author of BVI, gave last fall semester. Okay, now we come up to these security considerations. So we are extending the system with new processing execution capabilities or computing capabilities, and in the end we are placing processing elements closer to the memory, and we may have different processes using these processing elements, right? So this creates new security concerns that for sure we will need to deal with. But also, we cannot forget that this processing in memory systems give us also new opportunities in terms of security, right? And in that sense, processing in memory systems can also be used to support new security primitives that can make our system more secure and more reliable. And in that sense, our group has proposed several works to generate physically unclonable functions or random numbers in memory that can clearly benefit the security of the overall system, right? The first of these ideas, the DRAM latency path, is based on exploiting the random process variation that comes from manufacturing. In the end means that there are some cells that have high probability of high percentage of or chance to fail with reduced TRCD, while others have much less probability of error with reduced TRCD if we reduce the timing parameters here. And by taking advantage of this characteristic and the random process variation from manufacturing, it's possible to create physically unclonable functions that are repeatable and unique device signatures that can identify a system or can identify a DRAM DIMM and make it, let's say, trustable. This is the paper. And similar to the DL path, to the DRAM latency paths, is the D-range key idea, also based on random process variation, extracting random values by observing DRAM, and also taking advantage of the different probability of failure for the reduced TRCD for different cells, right? And based on that, it's also possible to obtain to extract random values from DRAM. And here you have the paper that was presented at HVCA 2019. And more recently, another proposal from more group also generates random numbers by using similar ideas to those exploited in the compute DRAM paper that I mentioned before. The observation here is that carefully engineered DRAM commands can activate 4 rows in real DRAM chips. Like when reducing the time and parameters, the latency between an activate and a pre-charge command and the next activate command, when using violating timing parameters, it's possible to activate 4 rows with these 2 activate commands. The idea is to have 4 different rows. Some of them contain 1, and the other 2 contain 0, and this is the steady state, let's say, where the voltage of the bit line is half VDD, and we have this threshold voltage, and the idea in this operation is to first, or in Quack, the idea is to first activate 1 row 0, then pre-charge before we reach the threshold voltage, then activate another row, in this case row 3, and then at some point we enable the sense amplifiers. So the point is that at this, the thing is that at this point in time, what happens is that we obtain a random perturbation, and this random perturbation can even go up or go down. That is, it can go to logical 1 or logical 0 in the sense amplifier, and this is a way of generating random values. So the idea is to leverage these random values on the sense amplifier generated by the Quack operations as a source of entropy. So this is what we call a DRAM segment for different rows containing 0s and 1s, as we have seen before. In the second step, we perform the quadruple row activation, and this generates the random values, logic 1 and logic 0s. Now what we do with the contents of the sense amplifier is dividing them into 256-bit Shannon entropy blocks, and these Shannon entropy blocks are used to generate the true random numbers, 256-bit true random numbers. So that's essentially the idea of Quack. And as you see, Quack is a very good example of how to generate random numbers in a simple manner using conventional DRAM chips, but also it's a nice way of showing what are the potentials of processing in memory to provide new security primitives that can increase and enhance the security of the whole system. Okay, something that we have also talked about in the course are benchmarks and simulation infrastructures, and that's also something very much important and interesting for enabling the adoption of processing in memory. Why is that? First of all, we need simulation infrastructures to explore or research ideas, to try if they are good or not, to find what are the cases where they are good or not. And also we need benchmarks, first of all, to run on these simulators for us to see what are the potential performance and energy benefits from our architectural proposals, but also to compare real systems, and also, why not, to serve as examples for future users as well, and future programmers of these processing in memory systems. And this is why we have worked in this direction as well, and why we have covered this direction in this course as well. And one good example are the PIM benchmarks that I presented a few weeks ago. Remember that here we have a collection of 16 benchmarks from different fields like dense and sparse linear algebra, databases, data analytics, etc. And these benchmarks are open source and publicly available in our repository, as you can see. But PIM benchmarks are not the only one. Here you have also a lecture where I presented and discussed the analysis of these PIM benchmarks on the UPMEM PIM system. But as I said, these PIM benchmarks are not the only ones that we have developed. We also presented in this work the DAMove work, a new methodology and benchmark suite for evaluating data movement bottlenecks. And here it's not only the methodology to characterize the bottlenecks, and remember that we found 6 different classes of bottlenecks. Some of them can be very much alleviated by using processing in memory capabilities, but well, in some cases it depends on the specific workload. In other cases, we found that one of the classes is compute bound, and these kind of applications are better to be executed on the host system. They don't really benefit from processing in memory. But yeah, as I said, not only this methodology to characterize the workloads, but also a product of this method of this work was the benchmark suite with more than 100 benchmarks that are publicly available as well, and the simulator that we used in this study. So you can find all of that in the paper. You can find everything in the repository as well. And remember that Geraldo presented the move in meeting 7, if you want to check it for your own reference. It's not the only simulator. The DAMove simulator is not the only simulator that we have publicly released. Before that, a couple of years earlier, we also released the processing in memory version of Ramulator. Ramulator is a widely used DRAM simulator. We extended Ramulator to support PIM operations. And there are also other nice simulators from our group that are also publicly available, like, for example, MQSim, that is for SSDs and can also be extended for processing in memory or processing in SSD. But simulators might not be the best solution, depending on what we want to explore or what we want to experiment with, right? Why is that? Because in the end, a simulator is a relatively bulky tool that needs to run on a CPU, and simulating a whole system by a program that runs on a CPU might take a lot of time, right? Even though it's very good, because we are going to obtain a lot of details, a lot of metrics and insights. We will be able to generate insights from our simulation results. It might not be the best solution in all cases. That will depend on what is the specific purpose that we are targeting. For example, if you want to figure out whether an application is good or not for processing in memory, and you don't have access to a real processing in memory or to the type of processing in memory that you want to evaluate, then you need to use a simulator, right? But if instead of one specific application with one specific data set, you have thousands of them, then doing this analysis on a simulator might take too long, right? And in these cases, if we are able to come up with some simpler models that can already provide insights on, for example, PIM suitability, that's going to be much better. And that's what we tried in this NAPL work that provides a performance and energy prediction tool based on machine learning, in particular based on ensemble learning. Let me very briefly introduce you to this NAPL work. So the motivation is, of course, to use processing in memory or near memory computing, which is essentially the same thing as the different name for the same thing. The problem is that simulation times are extremely slow imposing long runtime, especially in the early stage design space exploration. For example, if you want to try new architectural ideas, or as I said before, if you want to explore the processing in memory suitability or a particular workload, simulation might take too long for our goals. So our goal in this work is to provide a quick high-level performance and energy estimation framework for processing in memory architectures. And that's our contribution. NAPL, a fast and accurate performance and energy prediction for previously unseen applications using ensemble learning. So this works with completely new applications that we haven't used to train the ensemble learning method or something like that. We use intelligent statistical techniques and microarchitecture independent application features to minimize the experimental runs. And in our evaluation, we observed that NAPL is more than 200 times faster than a state-of-the-art processing in memory simulator, with also very low error rates in terms of performance and energy estimation. So as we have seen before, simulation for design space exploration on analysis of workload suitability. There are several simulators out there, but all of them are pretty slow, right? Up to 10,000 times slower than the execution on a real system. So that's why we want to leverage here the ML with the statistical techniques in order to be able to do predictions in a much faster manner. So NAPL has two sides. I mean, first of all, we need to train the model, and then we will do inference. Let's first of all take a look at how we train the model. In the training, we have a phase one that is it's an LLVM-based kernel analysis that essentially obtains information about the instruction mix in our program, about the memory behavior, like for example, how memory intense is this workload, or other metrics like instruction level parallelism. And we have a phase two where we do microarchitecture simulation. First of all, we generate traces from our program, from our application, and then we do trace simulation. Here, in order to keep this microarchitecture simulation lightweight and not have to use a huge amount of data in our data sets, in our training data sets, we apply a technique that is called design of experiments in order to minimize the number of experiments that we need to do in the data collection. And then by using the information obtained from phase one and phase two, which are application features, and also the knowledge from the microarchitecture, like instruction per cycles and hardware features, we can train the ensemble learning algorithm. And then, yeah, so here among the application features, we have instruction mix, instruction level parallelism, reuse distance, memory and register traffic, and memory footprint. And among the architecture features, we have core types, number of processing elements, frequency, cache line size, DRAM layers, cache access fraction, and DRAM access fraction. So this relates to hits and misses in the cache hierarchy. So these are the characteristics that are used, or the features that are used to train the ensemble learning algorithm. And once the ensemble learning algorithm is trained, the only thing that we have to do in the prediction is to apply the LLVM kernel analysis to obtain instruction mix, memory behavior, ILP, and these application features from our new application, feed them into the prediction model, and directly obtain performance and energy estimates that are based on our model and based on the previously and the training that we did previously. So this is the evaluation methodology. Here we used, we compare to a state-of-the-art simulator. By that time, it was Ramulator PIM, the processing in memory version of Ramulator. And we used different workloads from Polybank, Rodinia, benchmark suites. And here you can see, so this is like the NAPL accuracy in terms of performance prediction, and in also the energy prediction. NAPL is the darker blue bar, as you see in if not all cases, almost all cases, NAPL performs better than decision tree and an artificial neural network. So as you see, pretty accurate for the performance and energy estimates. And also pretty fast. You can check the details in the paper, but on average, 220 times faster than the state-of-the-art simulator, and up to more than 1,000 times faster for some of the workloads. And we also include one use case in the paper that is a processing in memory suitability study. Yeah, so and we also observed like very good accuracy in terms of prediction, right? So actual EDP reduction here is the lighter blue on the simulator, and this is what we predict. The darker blue is what we predict with the NAP. And this is the paper presented at DAC 2019 and part of the PhD thesis of Gagan. Okay, yeah, I think we are close to the end. Thank you very much for attending this long lecture. One of the things that processing in memory also enables is to, discover new applications that can benefit from processing in memory and can greatly increase their performance and reduce their energy consumption based on processing in memory. And this can enable even new applications. So, for example, this green filter is a proposal for seed location filtering in DNA read mapping using processing in memory. This kind of proposal can enable new use cases for many applications. If you are able to perform one particular application or execute one particular algorithm much faster in a processing in memory system, and also do it saving a lot of energy, you are probably enabling new use cases. Like, for example, being able to perform sequence alignment and read mapping operations in in mobile devices that can be pretty useful in certain environments. In the end, well, in this particular case, green filter works with one of the stages of the genomics pipeline, that is the filtering step. The idea is to accelerate this filtering step and accelerate the read mapping operation, that is approximate the stream matching problem. And this stream matching problem is pretty costly. It's very expensive, right? By doing it in memory with the green filter, it's possible to greatly accelerate read mapping and by reducing the number of required alignments. And as you can find in the paper, it provides a speed up of up to 3.7 times with respect to the baseline processor. Another related work here is GenAsem. It's as well a new algorithm and also a new accelerator, processing in memory accelerator for accelerating approximate stream matching in sequence alignment. Or in another work, this one, Google Workloads for Consumer Devices, presented at ASPLOS 2018 and part of the thesis of Amirali, we here also showed how processing in memory can be very beneficial for consumer mobile devices, and how important applications in these consumer devices, like, for example, video encoding and video decoding or neural networks, can be greatly accelerated by using processing in memory capabilities. Or how to accelerate climate modeling, another proposal, and near processing in memory or near HBM memory accelerator for stencils to accelerate the Cosmo model for climate modeling, also part of Gagan's thesis as well. Or this NATSA, another processing in memory accelerator for time series analysis, a class of applications that have or a class of algorithms that have applications in different fields, like, for example, sequence alignment, medical applications like electrocardiograms, or even earthquake detection, and so on. In the end, whatever has a time series that needs to be analyzed in a fast and efficient manner can benefit from this kind of accelerator, or at least the execution near memory, because these are very highly memory intensive applications. Okay, so yeah, I guess that I covered most of it. Now it's like the time to for the epilogue, time to conclude this lecture, and also to conclude the course. Observe that over the course of these 12 weeks, we have covered many different topics related to real-world processing in memory architectures, how to program them, what are workloads that can benefit from processing in memory, how to identify what are these workload characteristics that make them good or bad for processing in memory, and so on. And in the end, and also as I said in the beginning of the lecture today, our goal is to enable processing in memory, to continue doing academic research, to continue inspiring people to do their own research, and to come up with their own proposals to make to make this processing in memory paradigm real, to make it feasible, and hopefully at some point to find it in many more real world systems than what we can find today at the end of 2021. I'm pretty sure that in 1 year, in 2 years, we will see processing in memory capabilities in many more systems, from servers to mobile devices, and this definitely is going to change the way we compute and the way that we think about computation, and we plan for computation as well. Remember that first reference that I would recommend to everyone is this book chapter that we published this year. It contains a large and comprehensive summary of many state-of-the-art proposals in processing in memory, and also discusses many of the open problems and things that still need to be done in order to enable the adoption of processing in memory, as we have discussed in today's lecture. Remember as well that we have shorter versions of this book chapter, this older one, Micro, and published in 2019, and this other one that is more focused on workloads and programming is. Remember that processing in memory is a challenge and an opportunity for the future. The opportunity is to build fundamentally energy efficient computing architectures that are data-centric, and also not only energy efficient, but also high performance. The goal, the ultimate goal, is to create computing architectures with minimal data movement, and we are getting closer and closer to this ultimate goal. If you want to keep learning about processing in memory, I can recommend you many workloads, many talks from Professor Mudlu, like for example this one, Memory-Centric Computing Systems, and here you have the link to this workload. Highly recommended, as I said, and also keep tuned. Keep in touch with us if you want to discuss anything, you want to ask anything related to the contents of this course, or related to the research that we are doing in this topic. And I would like to invite everyone to join the next edition of the course that, as I said in the beginning, will take place in spring 2022, hopefully around end of February is when we will start. Okay, I think I don't see any questions in YouTube, also no questions in Zoom. So I just need to thank everyone for attending, for being interested in the different topics that we have covered in this course, different aspects of processing in memory. I hope you enjoyed all these lectures, you found them useful and instructive. And I wish you nice holidays and a very good start of the new year. Thank you very much for your attention.